Okay. So, anyone ever see 2001: A Space Odyssey? So,
The one directed by
Stanley
Stanley
Kubrick,
Kubrick?
yeah. So it was a big sci-fi movie from 1969 or something. Um, so in the beginning, there's some proto-humans, and they're worshiping a monolith. That's what Arthur C. Clarke wrote the script, and it's this big block. Lith is actually stone, like in Paleolithic and so forth. So this is a big stone, but it's come over into computer architecture. A monolith is a single giant system. So in the late 60s, we had the IBM 360. And when you got an IBM 360, you got the operating system, but the operating system included an entire database. There was COBOL, there was Fortran, there was a user interface, a menu. So everything, the idea was everything that you needed was built into this one program. And you just had to like set up your own tables for whatever your data was and write a little COBOL code, and you were good to go. At the same time, there were other examples of this. Lisp boxes also tended to be like monolithic like this. And there's an interesting essay called Why Worse is Better. And the Lisp guys all disdained, the Lisp guys were at MIT and Stanford. And they all disdained what they referred to as the New Jersey guys. The New Jersey guys were at Bell Labs. And what the New Jersey guys kept doing was just building little pieces of software that kind of did 80% of the job that needed to be done. And then over time, they might improve it. So what were these guys building? C, Unix, awk, troff, trying to think of what other things, make, what else, sed, stream editor. These guys were building a bunch of little tools. They weren't all part of one elegantly conceived thing like these monolithic systems were. They weren't. They didn't sit down and do an entire design that made for a unified, elegant system that included everything the user would need and had it all done perfectly right from the start. Instead, they said, well, people need to have something a little higher level than assembly language. We'll build them this language called C. It's got all sorts of things that are lacking, but when we find out they need them, we'll add them as we go along. Finally, after about a decade, someone said, well, also C needs classes, and this guy started working on a language called C with classes, and pretty soon he changed the name to C++. So this was C++ came out of this design philosophy. Take something, make something that quickly works. What do we call that now? What do we tend to refer to that quick product?
Object-oriented programming.
Well, that's C++ is, but when we're just trying to get something, okay, the user needs something, we're going to get them as fast as we can. We're going to get them the smallest program that does at least part of the job for them.
Agile.
Well, Agile incorporates that.
Prototype.
Minimum viable product. That's like the big catchphrase now. This was what Bell Labs was doing in the 70s, doing minimum viable products. You needed an editor. Well, they did a stream editor. This was very good for teletypes. It wasn't until Unix spread to Berkeley that Bill Joy wrote a program called VI in like 1978. So Unix didn't even have a full screen editor until then. People would edit a line at a time, basically. You'd pull a line up, because a lot of people were on a teletype, and you didn't have nice screen displays like we have now. These things all gradually accumulated things. In particular, the Unix philosophy was not to build one, even the operating system itself was striking in contrast to what was out there, like IBM 360. The operating system, for instance, built into the operating system, there was no way to list the files in a directory or to tell what directory you were in. These were external programs outside the operating system, LS, PWD. So the core operating system just basically provided a way to run processes and manage a file system in memory, right? Manage multiple users. And everything else was an add-on program. And the idea was make each program do a single job well. So we have a program like grep, right? Grep searches for a pattern in files and is available across Unix. So let's say you get these back, and what you really want to know is just a count of how many things there were, not grep will list each line, right? So the monolithic way of building this is to keep adding features to the program. People want to know how many lines there are. Let's add a line count feature. People want just certain columns cut out, right? Let's add the ability to extract columns into grep. What the Unix people said was, no, make each tool do one small thing and do it well, and then make a way to bind the tools together. So we could grep for Unix, and we want to know how many times it occurs. We pipe it into the word count program. This is a pipe that connects the output of this program to the input of this. We want to know, we want to select out just a particular column. Well, we're not going to add that to grep. We're going to have a program called cut and say cut the fourth column and just put that out on the screen. This was the basic Unix tools philosophy. You build small tools that do a single job with a method of interconnecting them. So the relevance of that to us today is that in the 90s, we started building web servers. And what did people do? They built monoliths. They built a single big application that ran on a server, and this was what Amazon did. On the Microservices section of the course, there's a link to this history. So they may have been running many instances of this. I'm sure by the early 2000s, they didn't have a single web server, but there was a single application. They would just put up 100 of them or 200 of them. I don't know what their scale was yet at that time. And what did that application do? Well, it presented a user interface. It allowed a search. It presented details on products. It presented images of the products. It gave predicted delivery dates. It gave recommendations for things like the product. It went and authenticated your credit card. It checked and tried to actually schedule the delivery. And this was one giant application. And sometime around 2002, 2003, early 2000s, Amazon realized they had reached the end of this. They were making a change to the application. Every change would break something else. The application had become extremely complex, extremely hard to understand. And what they did was move to, and I am doing a theoretical construction. Next week's speaker, Tom Limoncelli, had some material on what Stack Overflow's actual architecture is like. And he showed us to that. Hopefully, he showed us that. Hopefully, he'll do that again. So we have something like a load balancer and so some front-end servers. And what these talk to are so today, you'll find that Amazon is running a host of things behind what looks to you like a single Amazon website. And there's probably more I'm not even able to think of. So if they want to find out they want to process your payment, that's being sent to a separate payment server. If they want to log you in, that's going to a separate authentication server. When they want to give you this, today's recommendations, that's going to a separate recommendation server to serve that up. When they want to see if they can schedule, when they can schedule your delivery, that's going to a separate shipping server. By the way, we need to track the time so we're not delaying Dennis. 19. Okay, 10 minutes. Excellent. So first of all, let's notice that what they did was essentially bring the Unix tools philosophy out onto the web. They said, design a bunch of separate components, each of which does a single job well, and have them talk to each other. Don't try to design one giant monolith. The next thing is that these things can go down and you lose. So if the shipping server goes down, and there's not going to be one, there's going to be a host of them. But for some reason, something hits the shipping servers in general. Someone released a bug to the shipping servers. What happens? The user can do everything except it'll say, sorry, we can't schedule your shipment right now. We'll get back to you by email as soon as we can and let you know when we can ship this to you. If the recommendation server goes down, you're still going to be able to do your entire order. You're just not going to get a bunch of recommendations for other things to buy. So as much as possible, separate parts of the system can be down and the user can still do the maximum amount of stuff possible. This is in contrast to the monolithic app. If something in the recommendation server, there was a bad Python indentation and they tried to run it and it came down, it brought down the entire web service. There was nothing you could do at all. Another benefit that came from this is that it's much easier now to divide up work into teams and have different people work without interfering with each other. So what Amazon's principle is 2 pizza box. Anyone heard of this? You don't have any team bigger than you can feed with 2 boxes of pizza. So once the team gets fed 2 boxes of pizza and they're hungry, you have to split it up into new teams. I don't know how rigorously. If you had one really hungry guy, that might make for a very small team. But this is the general idea, that you don't want teams bigger than this because the teams can meet, they can coordinate easily, and they can do their work separately. They can work. So when we had the Unix tools, right? When we wanted grep to communicate we're grepping for food to word count, all we had to know was that grep would write plain text to standard output and word count would read it. The coordination between these things is a little bit trickier, but what we have is increasingly standardized. So what we do is we build servers that serve an API. They serve an application program interface. The interface is well defined. It's as simple as possible to do the job. You don't want to make it simpler than it takes to get the job done. And what each of these teams can do now is make any changes they need to the internals of their service, whatever they want to speed it up, enhance it, as long as the public interface stays unchanged. This should remind you of something people who have been through 2124, right? The object-oriented programming course. Does this remind you of anything from that course? Classes that we have a public interface and then private implementation details that we hide from the world, right? This is the same principle extended out onto the internet. We publish an API and we try to keep that API as stable as possible. Then behind that, we're free to innovate and do what we want with our service. And we are even free to add new parts to the API, so long as they don't break the old parts, right? It's fine. It's when you go to change the way an old part works that you really get trouble. We have Dennis in a couple minutes. I just want to show you, give you a little tour of what this actually looks like in practice. Wall plate. So that's what I want. There we go. So we returned that list of models. So compare what we get back here. We have a list of models with a name, an ID, some documentation, and a place to go to run it. So notice we have bacteria, a model of bacteria with the toxins and nutrient levels. When we come to this front end, which is written in React, and we look here, we got a model of bacteria with toxin and nutrient levels. This is just a different way of displaying the same API return. And it would be easy to put this into an iOS app, into an Android app, but we give structured formatted data in a way that many different programs can use it without determining what sort of client we're going to have asking for this information. Is it a program? Is it a React app? Is it an iOS app? And this allows great flexibility on the client side in terms of how you want to interface with the information coming out of the API server. And then I just want to briefly show you the code that generates this, because it's really remarkably simple code. So we want API. So we call the URLs endpoints. I don't know. I don't particularly fancy that name, but it's caught on. So, as with many other things, until I'm the dictator of APIs, I just better use the name that everyone else uses. So to create, to get that list of models, Flask REST Plus just has us use a Python decorator. And a decorator is something that wraps a class or a function in something else. A decorator in Python is a way to avoid writing boilerplate code again and again. So if you look at the graphing capabilities in Indra, let's say, there's about a dozen different functions that have to do with graphing, and they all rely on matplotlib. Now, we could have rewritten each one so that it checks and sees, is matplotlib installed validly, and then run the function. So this would have been a bunch of boilerplate. Boilerplate comes from the legal profession where there's like just standard stuff you put in every contract. I, the party of the first part, will herein refer to Dennis, the party of the second part, as blah, blah, blah. And you just have this stuff that you just chuck it in every contract. This boilerplate code could have been copied into each of these dozen functions, and then we'd have to maintain it. Instead, we wrapped them with requires matplotlib. And that takes the boilerplate code, puts it in one place, and then if the boilerplate, in a certain point in the boilerplate, you say call the passed function, the function that's passed in. So this wraps the class in a bunch of stuff Flask REST Plus does to process the API route. And then you just throw in get and put, and then the actions you need for get and put, and we'll look at that here. So get models, we just format HTTP response in this format, model ID, name, doc, source. And we return that, and that's our HTTP response to the GET request. So it's simple to program when you're using a nice tool like this. And again, this is Flask REST Plus. We should mention what REST is. REST is representational state transfer. This is the way that EMU, for instance, is functioning, and Indra. What we do is we don't maintain a user connection and try to maintain a bunch of user state on a server. This is prone, you get disconnects, you're going to time people out, right? Whenever you're using a web page and they say, whoops, you timed out. They were maintaining some state for you back on the web server, and they can't maintain that forever, right? They don't want to have because what'll happen as people keep coming in, they're going to fill up the web server memory with all these connections. At some point, they've got to say, oh no, Sabrina went away. She's not connected anymore. Let's disconnect her, right? So this is, if you're maintaining state, you've got to drop connections at some point. Representational state transfer says that what you're going to do is transfer everything you need to know for the transaction back and forth across the web. So, for instance, when we're doing our assembly language emulator, we pass an entire virtual machine to the web browser, and then the user does something and types in some code. Then we transfer the entire virtual machine and the code back to the server. It runs the code, that sets the virtual machine in a new state, and then we transfer the whole thing back to the web browser. So the entire state is transferred back and forth. If someone got this transfer, walked away from their computer for 5 years, came back and said, oh, run one more instruction, it would work, so long as we hadn't brought the server down or changed the API. So the entire state of the interaction between the server and the client is transferred back and forth in a REST API. And this makes for much more robust, more anti-fragile processing because you're not trying to maintain the state of multiple clients in the server. The entire state transfers to the client. Now the client holds the state, modifies it however they want, and sends it back to the server. So that's what the REST is in Flask REST Plus. Okay, so should we see if we can get Dennis?